Hello everyone and welcome to the last few sessions of the NPTEL course Machine Learning for Core Engineering Disciplines. Throughout the whole course we have developed an intuition about how machine learning works and we have looked at various complex algorithms. Now the time is ripe to look at some tutorials of neural networks to understand how they can be implemented through the use of Python and TensorFlow. We will look at both artificial neural networks, the regular feed forward type, and we will also look at recurrent neural networks including GRUs and LSTMs, which also we have briefly covered in the last few lectures. So let's go ahead and get started with this tutorial. So this tutorial will be about supervised machine learning with neural networks, and I would like to thank my teaching assistants Dr. Manas Sharma, Shivam Chaturvedi, Manasi Lavekar and Amar Krishna Gopinath for their help with the entire course. So we will start today's tutorial with learning how to apply different neural networks for supervised machine learning applications, and we will explore a number of different neural network algorithms, including the plain or vanilla neural network, the basic neural networks, vanilla recurrent neural networks, then long short term memory or LSTM for short, which we studied in the last few lectures, as well as gated recurrent unit, which is a lighter weight form of a recurrent neural network which has fewer parameters as compared to an LSTM and is faster. We will also look at combining a gated recurrent unit with an artificial neural network or feed forward layers to actually take the sequential features from an RNN and perform a lot of nonlinear operations on it to make predictions of our required target variables. So let's go ahead and get started. In the first part of the tutorial, as I said, we will work with just the vanilla neural networks. So this will be part 1 of the tutorial, and in part 2 of the tutorial we will look at all these recurrent neural networks, right, and we will use different data sets in part 1 and in part 2. Right. So in the first part we will demonstrate how to build a neural network regression model to predict house prices, and for that we will use the Boston housing data set. Right. So this is now a data set which is slightly removed from engineering, but it is more from daily life, wherein one wants to understand the pricing of properties or houses, right, and that will of course depend on a number of factors such as where the property is located, how large is the house, right, how well it is connected, is it near any transportation like airports and railway stations, and so on. Okay. Now this particular data set contains 13 numerical features for each suburb in the city of Boston, used to predict the median value of owner occupied homes, which is the target variable. Now this is a description of some of the features. These include the per capita crime rate, right, higher crime rates obviously reduce the housing prices. People like to live in safer localities where there is policing and there is access to safe places. Then the other feature is proportion of residential land zone for lots over 25,000 square feet. Higher values indicate more spacious suburban areas. So there is a lot of place for people to do outdoor activities. So then that includes higher prices. Then pollution is an important factor. So if you want to look at nitric oxide concentrations in parts per million, that is also an important factor, right. If you go to higher pollution levels, they can negatively impact housing values. The other features include the average number of rooms per house. Obviously more rooms indicate a larger, more expensive home, and then the weighted distance to 5 of Boston's employment centers. So greater proximity will be favorable, whereas greater distance may decrease the housing demand, right. So these are just some of the 13 features that we have discussed here, 5 of them, and these features include various socio-economic, demographic, geographic and housing related factors which together influence the median home value, right. So as we always do, we have to get started by importing all the essential libraries for building and evaluating our neural network regression model. So we will import the usual libraries like NumPy, Pandas, Matplotlib, and so on and so forth. We also need several utilities from scikit-learn, which include the train test split module, the standard scaler which we have more or less always used when deploying machine learning model, and also the metrics module wherein we want to calculate things like the mean absolute error, mean squared error, R squared, and so on. And as you remember, these are the important metrics to quantify the performance of any machine learning model on the training set as well as the unseen test set and any validation sets. Okay. So now here we are importing Tensorflow, right, which is one of the ways in which you can build neural networks. The other Python module which can also be used is PyTorch. So these are both options. In this particular tutorial we are going to look at Tensorflow. So now from tensorflow.keras we are going to import the sequential, dense, and all these kinds of modules, and we also import features to do early stopping, right. This was one of the things we had discussed, how early stopping can be a regularization strategy for neural networks. We also import this model checkpoint wherein we can save the model at various instances and then reload it at later points, right. So these are the types of layers that we want, we have imported, and then these are some regularization strategies as well as saving of the model. Okay. And we are going to set the seeds for reproducibility so that we get the same result if we run it another time on the same computer. Okay. So let's go ahead. So the first thing we have to do, of course, and this is standard, you know by now, is we have to split the data into training and testing sets and prepare that, right, for applying the machine learning model, right. So we are also importing this data set. Turns out that tensorflow.keras.datasets already includes the Boston housing datasets, so we can directly import it. And once you have loaded the data set, it also comes with the train X and train Y. So these are the features in the training set, this is the value of the target variable, right, the median house price in the training set, and these are the corresponding features and target variable values in the test data set. Okay. And of course you can using the shape property you can find out how many data points are there, right. So turns out that there are 404 data points in the training set and about 100 data points in the test set. So this is 4:1 ratio, so basically 75:25 80:20 split is being employed here. This also tells you the number of features, so the number of columns is equal to the number of features. So you know that there are 13 features in this data set, which is what we had discussed, and so therefore it's clear this is the Y shape. So obviously there is only one target variable, so it just consists of one target variable for each of the points in the training set and then one value for each of the points in the test set, right. So once we have loaded the data, you know that the other things that we do to clean up the data set is to remove the outliers. So here we are removing, right, any data points with very large house prices. So let's say we only want to develop a model in the range of lower house prices, or let's say that you found that there's a lot of outliers in the model. Once you plot it, you can remove them. And the more important thing, of course, is to do feature scaling, right, which we have been doing all the way so far. Here we are using the standard scaler, which will standardize the input features to have a mean of 0 for every feature as well as a variance of 1, and this sort of helps you handle each feature on an equal numerical fitting. It's not that any one feature will have a very large value and therefore it will start to dominate the neural network, right. So this ensures faster, more stable model training. Alright, so this is the code to do what we just said. We removed the outliers, we have standardized the features using the standard scaler. Remember that once you find out, right, the transformation to zero out the feature values and the divisions to make the standard deviation and variance 1, you have to apply the same transformation on the test set so that the data in the test set, right, the features can also be scaled using the same standard scale. Okay. So once all this is done, this is by now hopefully very routine for you, you have done it multiple times. So what we can go ahead and do is we can build the neural network model. We are using a simple fully connected neural network model for regression where the input layer has 13 nodes because that matches the number of features in the Boston housing data set, and we are using 3 dense layers with ReLU activation. Of course you know that these are hyperparameters of a neural network, the number of hidden layers, the type of the activation function, all these are hyperparameters, and you may actually have to tune these to obtain the best performance from your machine learning model by doing cross validation or by simply using an unseen validation set. Now here in the output layer we have a single neuron because we have only one target variable and we are looking for a regression model. So we have chosen ReLU activation. Remember that a sigmoid activation gives always values between 0 and 1, tanh activation gives between -1 and 1, a ReLU activation on the other hand can take any positive value. Here we are interested in prices which are positive values, so we are taking ReLU activation in all the layers, and we have a single neuron for predicting the house price. Okay. So here again we have imported the types of layers that we are using, and this is where we define the architecture of the model, right, the number of nodes, right, in each of the hidden layers, right. So we are saying that there are 3 dense layers which we have used with ReLU activation, and these layers have 128 nodes, 64 nodes, 32 nodes, and of course the last layer, the output layer, you know, has only one node, right, because you only want one target variable. And the input shape, you of course know that there are 13 features, right. So the 13 features should come in to the input layer, and then these are the 3 dense layers with 128, 64 and 32 nodes, and finally you have the output layer with 1 node. In each of the layers we have also specified the activation function to be the ReLU activation function, and in the last layer, although we could have used a ReLU activation function to predict a positive value, we haven't done that. In any case, all positive values map to the same x, right. Whenever x is greater than 0, then ReLU of x is equal to x. So as such the activation won't do anything to positive values, so we don't need to use it as well. Okay. Then we have compiling the model here, and of course we have to set other options like what optimizer we have. And if you remember, ADAM is the adaptive moment estimation which we learned some 25 lectures ago or so. We are using the mean squared error loss, right, and we also want to target the mean absolute error as a metric that we want to evaluate once the model has been deployed, right. And finally, yeah, this command just tells you that we have to provide a summary of the model, right. So this tells you what kind of a system the model is getting trained on, what kind of architecture we are using, and this just tells you the number of parameters in the model. If you so basically if you remember, we are uploading all these PDFs as well as the Jupyter notebooks on GitHub. So if you open github.com/AGR group/nptel-ml, you will be able to access all the Jupyter notebooks as well as these PDFs. Why I want you to do that is you can run the code yourself, and of course some of the things which are getting truncated here due to the width of the PDF, you will be able to see these numbers in the Jupyter notebook. So I encourage you to download the Jupyter notebook for these tutorials from online and the PDFs, and you can do it at your own end. In any case, if you sum up all the parameters, we also have the total number of parameters listed here. So this is a model with 12,000 parameters. So you can see that the number of parameters really increases with just 3 layers, and therefore neural networks can be really expensive models, right. It takes a long time to train them, and inference can also be expensive, and this is why we have also studied some of the less expensive models like decision trees and so on, that support vector machine, decision trees, kernel ridge regression, GPR, Gaussian process regression, and so on. Okay. So now we train the neural network using the training set, and like I said, we are employing early stopping right, it stops training when the validation loss stops improving for 20 epochs. This is a regularization strategy to prevent overfitting. We also save the model as a checkpoint based on the validation loss so that we can retrieve the model later and we can do various things with it, which includes continuing the training process as well. Now we train the model for up to 100 epochs, which a batch size of 32, using 10% of the training data for validation. So here we are using a fixed validation set. Remember, there is also cross validation and there is a fixed validation set, and with neural networks, whenever there is a lot of data points, you can work with a fixed validation set as well, because it's very expensive to train these models, but for much simpler models, cross validation is almost always a preferred strategy. Okay, so now let's go ahead, right, we are importing early stopping and model checkpoint, and then we are describing, right, what do you have to monitor. You have to monitor the validation loss, and if it stops improving, right, for more than 20 epochs, then you stop, right, you do early stopping. And then this patience is something we had actually defined in the lecture. That's the point at which you stop waiting for the loss function to improve, right, to reduce, and then you just truncate the model. And of course there is a checkpoint, right, you have to save the best model. Okay, so this is giving some more of these parameters which we already mentioned. You are fitting the scaled x, right, and the y values. Then this is the validation split. 10% of the trained data you are going to use for validation, the total number of epochs, the batch size. This was all described slightly earlier in the tutorial. We are just putting in the numbers into the commands here, and then we obviously have to pass these objects here, the early stopping and the checkpoint, and verbose just tells that it should print all the things that are happening here. Okay, so what I have done here is I have actually removed some of the text from epoch, so you will not see the epoch start at 1, right. I am directly starting at epoch 76. That's because there is a lot of text here. Obviously if you download the Jupyter notebook, you will be able to see all the metrics, but you can see here that it's not necessary that the validation loss comes down, it can actually go up, right. So these kinds of things are possible. So I encourage you to download the Jupyter notebook and monitor how the validation loss comes down, right. Once we have fit the model, trained the model, we are then evaluating the model's performance on both the training and the test data sets. So these are things that you have already seen before. We are making predictions using the model that was just trained, using both the scaled features, right, in the train set and the scaled features in the test set. Then we can compute the metrics, again these kinds of things, right. This is done through the metrics module of sklearn, and you know that it's really straightforward. There are all these inbuilt functions to compute the mean absolute error, the mean squared error, r squared, and so on. Although by now in the course you exactly know the expressions, how these should be calculated. So if required, you could even write your own Python code or own MATLAB code to do these kind of calculations. Okay, so once this is done, we are simply printing out the values of the train r square and the test r square, and then we are of course looking at parity plots. If you remember, parity plots are a very important way to evaluate the performance of the model, wherein on the horizontal axis you have the actual target variable values, on the vertical axis you have the predicted target variable values, and if the model was perfect, everything would be at the 45-degree line, the y equals x line, but because models are not perfect, there is always deviations from this 45-degree line. So here we are making, using matplotlib, the scatter plots of the train y and the train set predictions and the test y and the test set predictions. This alpha is just setting the transparency, you can set the color as well, and this is how we are making the plots. We are of course also setting the x label, y label, and the title. Okay, so this is how the parity plot looks. It's not bad, right. So you can see that there is some kind of an alignment around the y equals x line. On the y axis is the predicted house price in thousands of dollars, and on the x axis is the actual house price in thousands of dollars. Okay, so this is how the parity plot looks, which is good, and as we already discussed, we should also be monitoring the loss function as a function of the epochs, right, whether it's decreasing for the training set, whether it's decreasing for the validation set. This will allow you to prevent overfitting of the model, which is very common in complex models like neural networks. Okay, so to better understand the training process, we visualize the MSE loss function curves across epochs. So the training loss or MSE will show you how well the model fits the training data, and then the validation loss will show how well the model generalizes to unseen data. And this, like I already said, helps prevent or at least identify underfitting and overfitting, right, which should not be happening. So here we are simply plotting, right, the loss as well as the validation loss, and then we are using a log scale. On the x axis we have the epochs, on the y axis we have the loss, right. So you can see here clearly that the loss started, right, at a very high value. This is 100, this is 200, 300, 400, 500. So it started around 450 and then it's constantly coming down, and you can see that the train loss, right, the validation loss is slightly lower. Initially the train loss is higher, but then finally the train loss comes down. So in this case, at this point you can say that the model is sort of nicely fit, but after a while your train loss starts to fall over the validation loss. So this is an indication of overfitting, right. It's because the model performs very well on the training set but does not perform as well on the validation set. So in principle one could have stopped the model at 40 epochs. This is where the train and the validation losses are equal to each other. As you go further, you increase the tendency of the model overfitting. So clearly the plot of the loss function versus the epochs is very valuable in terms of identifying the problems of overfitting and underfitting, whether it's for neural networks or the various other machine learning models that we have learnt throughout this course. Okay, so this is where we make the switch over to recurrent neural networks. So by this point we have already studied how to use Keras and TensorFlow to train simple neural networks with feed forward layers, and we discussed a very simple architecture used to predict the prices of houses in Boston, and this was done using the Boston prices housing price data set, which is already available as an inbuilt data set. Okay, so with that out of the way, let's switch gears and move on to training machine learning models for recurrent neural networks. So why do we need to do this? While feed forward neural networks process inputs independently, right, each feature enters the model independently. However, when you are dealing with things like text, right, time series data, sequential data, audio, video, right, there is some sort of an order in which the features should enter the machine learning model or the neural network, and this is where the concept of recurrence, right, wherein you can feed the next set of features into the model, right, and keep on propagating that through the network, that becomes very valuable in such real world applications where the order of the data points is important, like time series forecasting, whether it is for stock prices, it's for weather, it's for the dynamics of electrical, mechanical, chemical or aerospace systems encountered in core engineering disciplines, or it is natural language processing, whether it's text, right, where when you are interacting with chatbots, or it's speech, which is voice assistants like Siri and so on can be used. And finally, if you have sensor data streams, and these are very important in plants, right, so whether you have a manufacturing plant or a chemical plant or a power plant, there can be time series of data, whether it is current over time or it is voltage over time or it is the temperature as a function of time, pressure as a function of time, concentration of serious and harmful pollutants as a function of time, and of explosive materials. So these kinds of things, it's very important to include the time series into the model, and therefore we are going to look at recurrent neural networks. These recurrent neural networks are designed to handle sequences, right. So unlike standard neural networks, RNNs have loops in their architecture, and this is something we looked at during the lecture series, and this allows information to persist across time steps. Of course, we also have ways in which you can make the model forget the very old data. So the extent to which the model or the number of time series over which the model remembers the older features is important, right. So that's like a hyperparameter and should be adjusted. So the memory that is possible in RNN enables the network to learn patterns that depend on previous inputs in the sequence, right. So what are the key characteristics of RNNs? These typically maintain a hidden state that captures information about the previous elements in the sequence. So what happens before is stored in a hidden state. So that's very important feature of an RNN. These use shared weights across the time steps. So the way in which the data is processed each time step remains the same, the weights do not change, and this allows one to process the data efficiently, and they can be extended with variants like the long short term memory as well as the gated recurrent unit, LSTM and GRU, which can handle slightly longer term dependencies more effectively. Okay. So in this part of the tutorial we will switch to a slightly different problem. This is a problem from material science which will be reminiscent to what we did in one of the first tutorials wherein we looked at nanopores or tiny holes in graphene. Now graphene is a two-dimensional material consisting of a single layer of carbon atoms. So this is just carbon atoms arranged in a hexagonal lattice. So each of these is a carbon atom, and you can see this honeycomb lattice here, right. So you can see the carbon atoms here and there is a honeycomb lattice, right. These C's are arranged in a honeycomb pattern, and this is a nanopore here, right. So this set of missing atoms here, it constitutes a nanopore, and nanopores have very important applications in things like carbon dioxide capture, seawater desalination as well as DNA sequencing. So it not only has biological applications, it also has chemical and physical applications, sensing applications and so on, right. So now what is the link of a recurrent neural network to a nanopore inside a 2D material, right. So obviously a recurrent neural network is used when there are sequences involved in the model. So here the sequence is arising because we are working with a language based representation of a nanopore inside a 2D material, which is called the string representation of nanopore geometry, strong. So this is a language that our group had introduced last year in 2024 to represent nanopores in two-dimensional materials, right. And the target variable here is the formation energy of a nanopore, right. So because these nanopores have different shapes, each one of them will require a different amount of energy to form. So we are trying to relate the shape of a nanopore as quantified by a string representation such as the one given here with the target variable, that is the property, right. So from this feature which is just text, right, this string representation, we want to predict the target variable which here is the formation energy, and therefore we have to use a recurrent neural network. Okay. So in this strong language string representation of nanopore geometry, you have various characters, you have different types of atoms in the graphene lattice. These include fully bonded atoms, so atoms which are surrounded on all three sides, right, by other atoms. These are called fully bonded atoms, or F. Then you have zigzag atoms, right. So here the zigzag atoms are shown in this color, green color. So this is zigzag. Then you have armchair atoms shown in red color here. This is an armchair atom and this is an armchair atom. Then you have corner atoms here shown in blue color. This is a corner atom, and then you have a singly bonded atom which forms only one bond with the edge, right. So you have different atom types, and what we have done here, we have started with the white arrow here, and then we are just traversing the nanopore, right, going around the nanopore and just noting down the type of the atom that appears, and by noting this down in sequence we have come up with a unique name of a nanopore in graphene, right. So this is the sequence we are working with. So there is a strong representation, string representation of each nanopore as explained in this figure, and we want to predict the formation energy of the particular nanopore. So this is therefore a regression problem with sequential input, and we will work with the so called canonical strongs, right. Now if you see this nanopore, it does not matter which atom you start with. If you wanted to write the name, you could start with here, you could start here, or you could start here, and the name of the nanopore should be the same. So whether you start here or here, the name of the nanopore should be the same. So what we do is we come up with a standard form, a canonical form, wherein the cyclic permutation of the strong which appears first in an English language dictionary is the strong that is considered for each nanopore. So in other words, if there is an A, you will preferably start with an A. If there are two A's, you will start the strong at the two A's, right, and then write it from there. So in this case you will write it as AA, FF, ZFF, right. So basically once you reach this end, you start here and go forward from the previous end, right, because like I said, it does not matter where you start. This is a cyclic representation. So what I have done here is, if you want the cyclic permutation that appears first in the English language dictionary, A appears first in an English language dictionary, and AA is even further starting towards the beginning. So we start with the AA, we reach FF, and once we reach FF we go back to the beginning. So that is where you get the ZFF, Z, and then you can write it and so on. So this particular form which would appear first in an English language dictionary is called the canonical representation. So this means that now every pore will have a unique strong, whereas earlier when we were talking about cyclic permutations and the fact that we could start from any of the atoms, it meant that every pore could have a number of strongs, right, whereas with the canonicalization we have ensured that every pore is mapped to one particular strong. Okay. So what we will do now is we will conclude this tutorial at this point. In today's tutorial what we did was we introduced the concept of training neural networks through the use of TensorFlow and Keras, and we first looked at a vanilla neural network, artificial neural network with simple feed forward layers, and this was applied to the Boston housing price data set, and we also looked at how we can do early stopping to prevent overfitting and to improve the generalizability of the model. We also looked at tracking of the training loss and the validation loss as a function of the number of epochs. We looked at how we can make parity plots, we can predict metrics like the mean absolute error, mean squared error, R squared, and so on. And next we introduced a data set corresponding to nanopores in graphene, a two-dimensional material, wherein we want to link a string representation of each nanopore to the energy it takes to form that nanopore inside the material. So in the next tutorial, which will be the last session for this NPTEL course, we will look at various recurrent neural networks including GRUs and LSTMs and combinations of GRUs with artificial neural networks to predict the formation energies of graphene nanopores. Thank you for joining today, and I look forward to seeing you next time.